Cloud.
So now I need to stop saying incriminating things, is what you're telling me.
Important. Okay,
We
so now
will edit the recording.
Oh, good.
If you want.
we got to hire an editing crew. But anyways, I think everyone's here. So today we have our good friend Zach talking to us about stochastic games for PDEs. I think most of us know Zach, so it's all yours. You can say whatever you want now.
Okay, well, hopefully you guys all know me, and if not, you'll know me quite well enough by the end of all this and my sense of humor. So I guess before I start talking, I want to go ahead and thank Nathan and Fudong for inviting me to give a talk here. Hopefully everybody will take something away from this. I think that stochastic games for PDE are incredibly fascinating, and there's a lot of work going on right now, which really is very relatively new. I believe that they're actually, maybe the breakthrough paper was within the past 20 to 30 years that made the connection that we are now using to actually solve PDE with this method. So it's all very fresh, it's all very new, and there's a lot of stuff going on. As you can see, I've got a lot of stuff planned for us. I don't know how much we're going to get through, so we're just going to play it by ear and see what happens. And basically, what I envision from this talk is I'm going to use it as a way to help you guys get at least a foot in the door of the theory, because it's very dense theory, which draws upon a lot of different tools and a lot of different ideas, some of which are not really very commonly taught until you specialize. So I'm going to hopefully make that a little bit more clear. As I say on this page here, I'm using mostly the presentation found in an entry in a book. The book is written by John Lewis, Juan Manfredi, Peter Lindquist, and I can't think of his last name, a gentleman by the last name of Salsa. And I can give you guys the information on that book. In fact, you can even download it if you're interested in reading more. I also use a few other papers to try and clear things up as needed, but we'll get to that later. So basically speaking, when we're talking about the aim of a stochastic game for PDE, what we're trying to do can be summed up in the following way. Every single time that a step size epsilon, which is small but positive, is given to us, we try to find a function v epsilon, which is going to satisfy the demands of the players. I'm going to get into that more, but essentially it's going to satisfy all the players of the game, and it's going to somehow represent the average value of the game. The next part is that you have to show that v epsilon for each epsilon satisfies some kind of mean value theorem, but discretized. We tend to call that the dynamic programming principle, although sometimes you'll also see people say the dynamic programming principle is the discretized mean value theorem, and it also is some kind of boundary value theorem or a boundary value portion. But in any case, we need both of those in order to make profitable comparisons. And finally, under the right conditions, we show that the family of functions v epsilon converge to some limit function, which is continuous, as epsilon decreases towards 0. And in a suitable sense, the viscosity sense, it turns out that v will be a solution to a related PDE for the game. Okay, it's actually not that complicated from this level, but of course that's because we're at the high up level. Now we get to go down into the weeds. That's where all the fun parts are. So the convergence that I'm talking about in item 3, that really is very complicated, and it depends largely upon the game that you play. Even though all these games follow the same basic rule book, every single one is slightly different. And so because of that, you sometimes need some kind of conditions on the domain that you're playing in. For example, exterior cone property sometimes is required. And I'm not going to really touch upon that. So instead, I give you guys a couple of references that you can look at. We will, however, talk a little bit about viscosity theory, since the solutions we're getting are viscosity solutions, and that will be closer to the end of our talk. The items 1 and 2 are the places where we're going to spend the most time. What we'll do then is we'll kind of introduce the tools we need in order to make sure that 1 and 2 bear fruit for us with our games. And then we'll proceed from there to talk about a couple of example games, and then we'll examine how we use the tools that we introduce in order to get the functions v epsilon that we need. So the very first thing we need is a definition. The definition is pretty easy. We have a probability space with a sigma algebra sigma. We also have a sub-sigma algebra theta. And we have some kind of random variable, which is to say an L1 function over the space F with respect to sigma. And so what we're going to do is introduce a function, a unique function, which we sometimes denote by G, and otherwise we denote by this E notation, which is the conditional expectation of F with respect to theta. You can see the equation down below that defines the function and tells you how it behaves. But the most important thing to understand here is that because of the way that we have assumed F behaves, we can't automatically restrict F to the sub-sigma algebra theta and still have a measurable function. You may not have that happen. In fact, generally, you probably won't have that happen. So in essence, what we're trying to do with this conditional expectation is produce a theta measurable function, which still has some kind of close relationship with F. And in particular, what it does is it shares the same averaging property as F. That's going to be really crucial for us because when we're doing these games, we're thinking of omega as being a set of data. And so sometimes we need to restrict that data, restrict the way the data works for us by changing the sigma algebra that we're working with. And I have a couple of quick examples here, at least one of which comes directly from the paper which I'm using for my presentation. They're both pretty straightforward, and I'm not going to dwell on them, but I'm going to flash them in front of your eyes because I like to make sure that you guys at least have some idea of what it is I'm talking about. So now once we have conditional expectation, what we can do is turn our attention to sequences of functions which are related to one another by that conditional expectation. So we have another definition. So once again, we have a probability space, and this time we have what we call a filtration of sub-sigma algebras, or a filtration of sigma algebras. For every single one of these sigma algebras, sigma n, we're also going to have a random variable, and the random variables are going to be related by their expectations. In particular, we say that the sequence xn is a martingale if for every single n, the conditional expectation of xn plus 1 with respect to sigma n is just xn. In other words, once we in order to restrict xn plus 1 to the previous sigma algebra, sub-sigma algebra, we find that all we have to do is use the function xn. And if we replace equality at the end of that definition by either of the two inequalities that you see below, we wind up with sub and super martingale definitions. I also have some examples of martingales real quick. Every single one of those is an easy example, and I'm going to let you read over them. And I'm going to also take that time to talk a little bit about why we're going to use it, because we will discuss that more in depth later. But the important thing for now is just to have some kind of idea of what I would do with this. And the idea basically is as follows. We are going to eventually take the positions that our game assumes as we move through a domain, through steps until we get to the boundary. We're going to show that at the boundary, we're going to get certain properties. And then what we're going to do is use the martingales to walk those steps and those properties back from the boundary into the domain D of interest for us. That way we can show that the properties that we're seeking apply not just on the boundary, but on the interior of D as well. And that's crucial. You can't really do that easily without the martingales. The definition also gives us a couple of really easy observations. And they are as follows. If xn is a martingale, then the expected value of xn is always equal to the expected value of x0. If you have a sub-martingale, then the expected value of xn is greater than or equal to the expected value of x0. And if xn is a super martingale, then the inequality is reversed. All of those things are going to be crucial as well. And this basically at the bottom summarizes what I was saying a minute ago about transferring properties from one part of the martingale to the next. Of course, part of the issue here is we need to actually be able to say when the martingale gets to the point where we need to employ the expected value properties we saw on the previous slide. And as I hinted, that's going to be on the boundary. But it's hard for us to know when that martingale is going to reach the boundary. So in order to be able to find out when it reaches the boundary, we have to introduce something else, which we're going to call a stopping time. For us, a stopping time is going to be another random variable, which we usually denote by tau. Tau is going to take values in the set 0 union with the natural numbers, and it's going to be called the stopping time with respect to the filtration sigma n, whenever we can say that the set where tau is less than n belongs to sigma n. In other words, when we put that upper bound on tau, automatically we're restricting ourselves to one particular member of the filtration of the sigma algebras. And that's the sense in which we're stopping our process. Now there's a whole bunch of properties, but we don't need every single one of them. Some of them are more interest if you were going to go deep into the theory or maybe do more stuff with probability. For us, we only really need the following, each of which is captured in the paper, which I call M. So the very first thing is that if tau is constant, then it's a stopping time. And if tau 1 and tau 2 are stopping times, then the maximum and minimum functions for tau 1 and tau 2 are also stopping times themselves, which has an immediate corollary. If I have a stopping time tau, then it is the limit of an increasing sequence of stopping times tau wedge n, the minimum of tau and the constant stopping time n. I'll also say one more thing here, because I feel this is one place where the presentation in M is a little bit sparse. When we're playing these games, we're going to introduce tau, and we're going to talk about it as if it's a stopping time. But so far in the presentations I've seen, I haven't seen a proof yet that has completely said to me, yes, in all cases, tau as we define it is a stopping time. So instead, what we're going to end up doing is using this corollary fact down at the bottom. Because since tau is a random variable, what we can do then is we can simply employ Fatu's lemma using this observation that tau is the limit of an increasing sequence of stopping times. We simply pass to the limit and use each of the intermediate stopping times, even if tau itself does not behave exactly the way we want. Also, and I'll go ahead and pause for a moment to note this here, I talk a lot. I have a lovely voice and I know it. So if you guys have questions, please feel free to pause me for a moment and say, hey, why the heck does it do this? Because I'm not going to slap you across the face verbally and say, no, I will stop and answer your question as best I can. We also have another lemma. First of all, we have to define what we mean by the sigma algebra sigma tau. And basically what it means is it's a sigma algebra. It's part of the lemma, actually. This is a sigma algebra. And it's composed precisely of the elements of sigma so that when you intersect each of those elements with the set where tau is less than n, the result is a member of the sigma algebra, the sub-sigma algebra, sigma n. And that has to be true for every single n, not a specific one, but all of them. With that definition, then, we can actually show that sigma tau is a sigma algebra. We can show that if tau happens to be the constant stopping time, then sigma tau is nothing more or less than sigma k, the subalgebra. If tau 1 is less than or equal to tau 2, and they're both stopping times, then sigma tau 1 is a sub-sigma algebra of sigma tau 2. Tau itself is sigma tau measurable. And the set where tau is finite is actually a measurable set under sigma tau. And Hayden, I agree with you to a certain extent right there. This stuff is all very technical and doesn't really tell us where we're going. Not to call you out, but let's be real here. It's technical. It's not fun yet. We'll get there. We also have another lemma. If we already have a martingale with respect to our filtration and we have a stopping time, we can define a stopped martingale, which is x sub tau of omega, which we define to be x sub tau of omega. And that is going to be giving us a random variable on sigma tau, assuming that we restrict ourselves to the sets where sigma tau is finite. And finally, we have what we really, really need from this theory, which is Doob's optimal sampling theorem. So Doob's theorem is given kind of, I guess, in an over-the-top way here. We don't need the full power of Doob's, but it's nice to have it in front of us. Effectively, what Doob's says is that the properties of martingales that we've already talked about, in a sense, transfer over to the stopped martingales, which is important to us. But more important to us, even than that, is the fact that we have this corollary. If in the corollary above we let tau 1 be identically 0, and if we let tau be tau 2, then actually we get exactly the property that I was mentioning a moment ago. Everything in Doob's theorem simply reduces down to the familiar martingale setting before, with the only difference being instead of expectation of xn, it's expectation of x tau. Good so far? I saw at least one nod, so that's good. Now, at this point, we've got everything we need from stopping times and martingales. So now we have to talk about infinite product spaces and their measurability, whether or not we can introduce probability measures on them. So of course, we already know a little bit, if we've taken our real analysis, about product spaces of measure spaces. And I'm just reminding you of that down here. No need to dwell on this for too long. I just want to make sure we're all on the same page. But for our case, we actually need something a little bit stronger. You see, basically our game is going to involve stepping from one spot in a domain to another spot in the domain, which is a distance of at most epsilon away from our previous spot. And since that spot, the new spot, is going to be chosen randomly, at least in some sense, it becomes totally possible that the path that we end up tracing throughout the domain is going to be infinitely long. As a consequence of that, we're going to end up dealing with infinite products of spaces. And we need to be able to say for sure that there is a probability measure that has the properties that we want on that infinite space. That is the goal of this section. And it's going to come down to a theorem of Komolgorov. So what we're going to do for right now is we're going to say that Pn is a probability measure, and it's defined on the measurable space Rn Borel sigma algebra of Rn. And we're going to assume then we have a family. The family is going to be consistent. And by consistent, what I mean here is that if I take the n+1th probability measure of the set A1 cross ... An cross R, the resulting measure is exactly the same as what I would get if I took the nth measure, the previous measure, and measured the once restricted set A1 cross ... cross An. A lot of times we simply say that Pn then is the marginal probability of Pn+1, and sometimes we use this projection notation, which I note down here. That sometimes is just useful in making sure that everything comes out smoothly and looks pretty nice. We're also going to define omega in this particular case to be, for us, the infinite product, the countably infinite product of the reals with itself. Or actually, really, this one should say here, and this is my bad, Rn with itself. The problem here is that we need the, each of these terms of the sequence omega to be a new position in Rn. So that is my bad. In your head, I think I can actually annotate here. Let me see if I can annotate this. There's a kind of a squiggly N. And there's kind of another squiggly N. There you go. It's perfectly fixed and nobody will say otherwise. Okay. In any case, omega is going to be the countable product of Rn with itself. And, thank you. We're going to say that F is the collection of all cylinders with base in Rn. With those two bits of notation and the definition of consistency, we're ready to introduce Komolgorov's theorem. Now I'm going to pause both to let you read the theorem because I don't feel like I need to read for you guys. I assume that you've gone ahead and passed preschool and middle school. But I am going to say to Nathan, Nathan, how the heck do you erase these marks here? Oh, yeah, never mind.
I don't know. You figured it out?
Yeah, I figured it out. You're superfluous now, Nathan. Thank you. Okay, the important thing from Komolgorov's theorem, which we'll also talk about in an extended sense in just a little bit, is that we can guarantee that when we have this infinite space, a space that's made up of infinitely many positions in Rn, we can not only make a sigma algebra over that space, which is cool, but so what, but we can also make for ourselves a unique probability measure. That probability measure will be defined upon the measurable space omega sigma, and moreover, if we then try to look at the marginal probabilities of this unique measure on the infinite space, it turns out to be just the transitional probabilities Pn in our family. That is going to be important for the theory. Nathan, it looks like you might have a question. You all good?
I'm good. I'm thinking about something related, but keep going. I'll ask it if I formulate it correctly.
Okay, that sounds good to me. So let's go ahead and check back into there. Okay. And this summarizes some of what I've been saying here. Each time we make a move in our game, thinking of this in a game theoretic sense, what's going to happen is we're going to pass from one point in Rn to another point in Rn. The sequence of points that we end up assuming as part of our game, the positions, end up forming a sequence which is possibly finite, but possibly infinite. To go along with that, we are going to end up defining our infinite measurable space and our infinite uniquely determined probability measure P. Now we've gotten past all the technical stuff, so we may celebrate because we're going to actually introduce a game for the very first time, which I feel like is important for a talk that has games in the title. Now, I've already mentioned this to at least a couple of people here, so for those of you who are here, you can tune me out for the next about 30 seconds or so, if you've already heard this. But there are really two perspectives here. One perspective is the perspective we really want to be able to take from now on, which is the game theoretic perspective. We simply talk about players, we talk about goals, we talk about payoff at the end of the game, and we talk about moving from point to point inside a domain, which we'll call D typically. That is a really nice way to talk about these games. It simplifies a lot of the notation and ideas down to something that you can almost picture in your head. However, we can't actually do that without also acknowledging the fact that there's deeper measure theoretic meaning going on behind the game theory. So what I'm going to do is I'm going to try to marry those two ideas in my presentation. Every single step of the game that I'm going to introduce, which is a very particular game, suited to a partial differential equation, which we'll talk about in a little bit. Every single step of this game is going to be first talked about in the measure theory sense, so we have an idea of what rigor is going on in the background, which lets us do the things we'll be talking about. And then it's also going to be talked about equivalently at each step in the game theory sense. So that way you hear what rigor is going on, but then you can also kind of picture what's happening in the game. My hope is that by putting those two things side by side, you'll understand this topic just a little bit better. Okay, so here's the very first part. And this part in black, is going to be common to both the game theory and to the measure theory. So what's going to happen is we're going to have a set X. X is going to be composed of both an interior and a boundary, or a boundary strip, as we'll see later on. At each and every single point in X, there is going to be a set of successors. The successors are places where we might possibly move at the next point in the game. One of the restrictions on the successors is that if you end up choosing a point in the boundary strip, then the successors bottlenecks down to simply that point and that point only. In other words, once you hit the boundary, we stop and we simply stay at that point. The game ends. We're also going to have a payoff function that goes from the boundary to the real numbers. We're not going to introduce too much about that right now because that will change depending upon the game we're playing. We're also going to introduce real numbers, alpha and beta, with the property that alpha plus beta is equal to 1, and they're both non-negative. At every single step, just to make this clear, when I say xn, I mean the n times product space formed from n copies of x. And by bn, I just mean the product sigma algebra because of that product space. Now, starting at some point x naught in the space, there is going to be a measure. That measure is going to be denoted by mu x naught, and it's going to be supported specifically in the set of successors, with the property that if you happen to choose a point in the boundary, then that measure is just the Dirac delta function, or the Dirac delta measure, I should say, at x naught. Now, with that measure in hand, that measure, alpha and beta, are going to induce a family of measures for us, which I call gamma of x naught, and you can see below. The important thing to note is that x1 and x2 are just points in the set of successors. And it can take any values in that set. We're not picking specific ones at this point. What's going to happen now is that we, or some force outside of our power, is going to choose a measure in that family. Just call it gamma x naught, little gamma x naught. And x1 is going to be a point among the successors that's chosen according to gamma x naught. We'll talk about that in a second. We'll also set the very first of our family of probability measures to simply be little gamma x naught. You can also think of it this way. There are two players, let's say me and Nathan, because he's the person whose mug I can see right now. We fixed a starting point somewhere in a domain D, or really somewhere in X. And what's going to happen is each of us has a strategy. A strategy for us is just a collection of mappings, and the mappings are going to tell us where we want to move next. Nathan has his own strategy, I have my own strategy. We may know something about each other's strategies, we may not at this point. And what we're going to do then is we're going to try to tell that game to move us to the point that we like based upon our strategy. At this stage, we flip a coin. The coin isn't weighted necessarily evenly. With probability beta, it's going to end up moving us randomly. But with probability alpha, what's going to happen is we're going to switch to a fairly weighted coin. We'll flip it, and if it's heads, then I get to move the coin wherever I want. And if it's tails, then Nathan gets to move the coin wherever he wants.
So repeat what happens for alpha, or for the first case.
Okay. So when we flip the not necessarily fair coin, what happens is we either move at random, which means in accordance with that measure that we talked about before, mu x naught.
Okay, I see. Yeah.
And if we end up with tails, then what happens is it splits down to being one of the two of us, and we simply move to whoever wins that fair coin toss's preferred point.
Okay.
The action of choosing x1 in that way automatically induces the measure little gamma x naught, which is important for us. Now what's going to happen is we're going to choose another measure it's going to be called little gamma x naught x1. So it records the history of the places that we've visited so far in our game. And it's going to be in the family gamma of x1, which is going to be analogous to the family gamma of x naught. x2 is going to be the next position of the game, which is chosen in the successors of x1, and it's going to be chosen according to little gamma of x naught x1. This time, though, we're going to make a slight difference. This part's a little bit tricky, but what's going to happen is we're going to make a probability measure with the property that it is consistent with the previous probability measure, which is the first part of what I've said here in blue. And the second part is, once we have a particular history, the particular history for our game positions is going to entirely determine how px02 measures rectangles and measures sets. That's what equation 3.1 tells us. Once we have picked our previous point x0, then we know how px02 behaves. On the much simpler side of things, from the game theory standpoint, we simply do what we did before, except this time, instead of being at x0, we're at x1. We apply our strategies again to figure out where we're going to move. We flip the unfairly weighted coin to decide if we get to choose or if randomness chooses. If we get to choose, we split 50-50 the chance of choosing where we move next between Nathan and myself. Now let's skip ahead some number of steps. We'll say n steps. So we already have the points x0 through xn minus 1 chosen. And we also have found the probability measures px01 through px0n. And they're going to be chosen in exactly the same way that we did in step 3. Now what we're going to do is we're going to choose a new probability measure. At this point, you should basically sense that we're having a pattern here. That new probability measure is going to be little gamma of x0 through xn minus 1. It belongs to the family gamma of xn minus 1. We're going to choose a new position according to that measure, and then we're going to make a brand new probability measure whose marginal probability is the previous probability measure, px0n, and such that once we have a partial history from x0 to xn minus 1, we have completely determined the behavior of x0 n plus 1. And I mentioned this at the bottom as well. That equation 3.2 is basically just a generalization of 3.1. All that we've done is assume that we have possibly more history available to us than we did in step 3. Once again, going minimal, step 4 from the game theoretic standpoint is exactly the same thing that what we've been doing before. The only difference is now that we're choosing an xn starting at point xn minus 1. Otherwise, everything is all the same as we've done before. Now what we're going to do is we're going to start building ourselves up to use Komolgorov's theorem. Well, actually, in this case, an extension of Komolgorov's theorem that's actually due to Tulsia. You can find the reference for that theorem at the end of my presentation. But we're going to, as before, choose omega to be the space of infinite sequences of points in X. We're going to be choosing sigma to be the sigma algebra which is generated by cylinders over the product spaces. And we're going to choose tau to be the infimum of the indices n such that xn belongs to the boundary y. In other words, tau looks at whatever sequence we have and immediately notifies us if we reach the boundary, which is not always a guarantee, and when we reach that boundary. If we never reach the boundary, we just assume that tau reports back infinity. But otherwise, it's going to be a finite natural number, or 0. At that point, at the point where we actually have a game that ends, or a sequence of points that ends the game, arrives at the boundary, then there's going to be a payoff. I'm going to switch to to the game theoretic standpoint for a second here and put it in these terms. If I simply say payoff, what it looks like is I'm talking about boundary data, and that's not wrong, especially from a PDE standpoint or an analysis standpoint, that is true. But from the perspective of myself and Nathan playing this game, actually it's a little bit more important. It's a little bit more of a desperate struggle. See, the thing is, he and I have wagered money on this game. So when this game ends, one of us is going to pay the other. Depending upon where the game ends is going to tell us who pays whom and how much. And that's going to be really important eventually, because right now it's just a little bit of setup. But eventually, we're going to have to consider how Nathan and I choose our strategies so that that way we can try to make the best out of this particular game. It's a strange thing, but it turns out that actually by choosing the strategy that you're going to play by effectively, and by sticking to that strategy, you can actually automatically generate functions, which are the var epsilons we talked about before, the family which is going to eventually converge to our solution. So the big question here, I'm sure, for all of you, whether or not I can see your faces, what the heck have we accomplished by doing all this? Yeah, we had some pretty colors. Yes, we had some steps. Yes, we kind of understand where this game went. But what does this mean for us? What have we done? Well, the very first thing that we've done is that we've ensured that we actually have a probability measure in this game. The game actually does conform to our measure theory, and so therefore we're going to be able to use tools like stopping times and martingales. That's essential for us. It would be super swell if we just played the game theoretically speaking, and never worried about the details. But if we did that, we wouldn't know for sure that we can do some of the things we're going to need to do. So this is a necessary evil for us. And as I mentioned before, we're kind of using Komolgorov's theorem here, but in fact, we're actually extending it. And the real theorem can be found in the book SV, which is referenced at the end. So that's the first part. The second thing that we've done is we've established that we can equivalently do all of the same formalism without actually having to explicitly talk about the formalism. The game that Nathan and I played for keeps, that game is good enough for our purposes. And so we can mostly drop the measure theory stuff unless we absolutely need it. And instead, we can just talk about it as a game. The one thing that we may have to do is we may have to talk about the measures, or we may have to talk about expectations later on. When we do that, we're going to always reference the strategies the way I did here. That family of measures that you're seeing in the middle of the board right now, that actually is the same as the family we had before. It just so happens that right now we are emphasizing the fact that the strategies that we have picked, Nathan and I, determine directly how the probabilities play out. And this is where we're starting to get to the juicy stuff, if we specifically allow X to be, say, some closed subset of the real numbers where D is a bounded domain, and we let Y be a strip which happens to contain the boundary of D, then actually we have an example game for the p-Laplace equation when P is greater than or equal to 2. And you can find the details of this more thoroughly written out in LMR, which is also in my references. So let's go ahead and repeat that. X for us, the interior, is simply going to be a bounded domain D. Y, the boundary from before, is actually going to be a strip. It's going to contain the boundary of the domain, but it's also going to contain points that are at most epsilon away from the boundary of the domain. So then we're going to assume the following things. The successors in our game that we were talking about before, well, those are just going to be points in closed balls, B of X radius epsilon. Every time that we talk about the measure mu X, really what that was is a normalized and restricted version of the Lebesgue measure on D. The function f for us in this case has to be both bounded and Borel measurable. And for us, we're going to pick specific values of alpha and beta, which are given right here. Those are necessary for the game to pay off the way we want. Under these conditions, excuse me, the game that we've just discussed actually is a game which discretizes, in a sense, the p-Laplacian. In other words, it discretizes this Dirichlet problem. So if we can do as I claimed at the very beginning, we can find a function associated with the game at each step epsilon. Our goal is to try and show that the functions, var epsilon, are actually going to eventually yield for us a solution of this Dirichlet problem, despite the fact that apparently all we've been doing is mucking about with betting. So never let anybody tell you that gambling is not worth your time. We actually also have another example. I mentioned it in the abstract, and so I want to throw it in here, although it's going to be of less importance for us. The exposition for this particular game is going to be just a little bit different, and so it was going to be too much to try and include it and a decent explanation of the game for the p-Laplacian. So I mention it here and give some idea of how it works without going into too many details. And as I say at the top, I'm completely ditching the measure theory at this point. It's there, it supports us, it'll be okay. We're just going to talk about game theory. So the steps now are going to be very, very familiar. There's only going to be one player this time is the first big difference though. T is just going to be the strategy of that one player. We're going to have a function which is going to be defined outside of our domain D, including on the boundary, but we're also going to be given a running payoff function f. And f's job is going to be to keep track of all the places that we've visited so far in the game. So this time, because I'm tired of gambling, I'm going to let Nathan do the gambling for me. And this is the important thing. That function f, Nathan, is going to keep track of where you've ended up moving in the game. So if you don't choose wisely, it's going to change how much you're going to have to pay me, the curator of the game, at the end, or how much I'm going to pay you. So you have to watch yourself now. At each point in the game, starting with the initial position and then eventually when you get to the nth position, your strategy is going to end up producing, instead of the next point explicitly, an orthonormal basis for Rn, and it's also going to have for each member of the orthonormal basis a scalar, which is going to take one of two values, both of them square roots of positive real numbers, little lambda and big lambda. I almost forgot my Greek. With probability 1 over 2n, and letting eta simply be either positive or negative 1, the next point in the game is going to be chosen randomly between the points xn, where we were previously, plus eta times whatever coefficient mu j is, times the jth member of the orthonormal basis. So, and I'm going to stop screen sharing for a second. Actually, you know what? No, I'm just remembering. I can doodle. I'm going to doodle for a second. So if we have a point here, let's say, and that right there is our xn, drawn by basically a preschooler, what you do is you simply choose arrows pointing away from xn in this direction and this direction. That's your orthonormal basis. Automatically, we know we could also move in the opposites of those directions. So it really is an orthonormal basis once we reflect. For each of those, you also automatically are choosing a length modifier. So the length can either be a little bit longer or a little bit smaller. The game randomly picks either one of these two or one of their reflections and the associated length you put with it and moves to that point. So if you have this game staged in R2, for example, like my picture would suggest, that means with probability 1/4, you're going to move up in the direction of that top arrow. With probability 1/4, you'll move in the direction of that side arrow. With probability 1/4, you'll move in each of the direction of the reflections. That's going to be the new position of the game. Let's erase that. Once again, once we reach the boundary, that's when the game ends. Now, it turns out in this case, we're going to simply change the notation a little bit, but the idea is still the same. We're simply going to be choosing a strip that's based upon not just epsilon, but also upon the values lambda and big lambda, which are defined previously before the game even has begun. Once we reach that boundary, though, that's when the payoff happens. So then at that point, we're going to have Nathan pay me, or I'm going to pay Nathan, according to the value of the function which is found by taking g at the point x tau, the point where you entered the boundary, and then subtracting away the sum here. And the sum is just going over all the points that Nathan visited on his way out of D into the boundary strip around D. This game goes along with this partial differential equation called Pucci's maximal operator for the choice lambda and big lambda. And in this particular case, because people absolutely love to be confusing, we also use lambda sub j to mean eigenvalues of the Hessian matrix for U. The measure theory is going to be a little bit different for this example game, but that's okay. As I noted before, now that we have an idea of how the measure theory plays out, even though it will be a little bit different, it'll be second verse, same as the first. A little bit louder and a little bit worse. And now I'm showing my age. There are a lot of points in my talks, whether I'm lecturing or whether I'm giving talks to you guys, where basically I have to ask for you the question, if you don't ask me yourselves, what the heck have we done here? Yeah, we've played a game. Why did we play this game? What is it going to do for us? How is that going to lead to our solutions? So I'm going to be impatient and I'm going to answer my own questions. There are two final keys to this puzzle, which depend upon the material we've already introduced. One of those is what we called the DPP before, and I'll remind you, the DPP, the dynamic programming principle, is sort of a discretized mean value theorem, which we're going to hopefully satisfy by playing the game. That's going to be crucial for us. The other thing is what we call almost optimizing strategies. Almost optimizing strategies are a very weird thing, but they're crucial for us. And we're going to explore both of those ideas, but we're going to focus on the game for the p-Laplacian, because as I mentioned, with details changing back and forth, we're either going to be dumping one of the two games, in this case, Pucci's operators, or else we're going to be standing here a very long time. And I figure all of you guys have got better things to do than listen to me for another hour or two.
Not really.
Are you really going to make me do extra work?
Yes.
That is what we call a jerk move.
Just
That
because
is
I can.
When we come back in January, I'm going to find you. I'm going to track you down.
In January.
Yeah.
Have a little confidence.
I have absolutely no confidence for this semester. Have you met people?
Yeah.
They're dumb. We're going to end up stuck inside for a nice long time.
Oh, I know. Yeah.
That's just how it is. That's people for you.
I know.
Okay, I'm going to stop haranguing the masses this way, and I'm going to actually move back to scholarly pursuits for a second. Now, basically, everything I've said here in the top part, everything I say here, I've already said a second ago. So I'm going to just clarify a little bit, and I'm going to give you an example. So if we go back to the p-Laplacian, it turns out that a function is going to be a viscosity solution, or once again, hold your questions, we'll talk about what that means, to the p-Laplacian if and only if it satisfies this equation right here. So as epsilon goes to 0, we end up having that u of x satisfies this equation here, which revolves around alpha, beta, the infimum of u along balls of radius epsilon, and supremum along balls of radius epsilon, and the average integral of u over balls of radius epsilon. Obviously, right here, we're kind of assuming that epsilon is going to go to 0 for us, so this is more of a continuous criterion. We don't want continuous, we want discretized.
Alpha and beta, so alpha, quick question.
Yes.
Alpha and beta depend on P, or?
Yes, they depend upon P, which for us is going to be fixed.
So if, just a question, if P is 2, you should get alpha is 0 or something similar?
Yes, in fact. Actually, there is a good paper for doing this. I have a whole bunch of good papers, but there's a good paper for doing this, exactly what you're suggesting, by Marta Luica and Juan Manfredi of Pittsburgh University. And they actually mention that if alpha is 0, then the problem exactly reduces down to nothing more or less than the classical Laplacian instead of being the p-Laplacian.
Mm-hmm. Okay, thanks.
We just like this because there's less known about the p-Laplacian. Also because the p-Laplacian is, and people will say this over and over again, I'm just repeating a script at this point, it is the gateway drug, if you will, to divergence form operators and divergence theory for those operators. It proves a lot of stuff for us and helps us exemplify a lot of stuff, which is very useful in modern PDE for nonlinear second-order equations. All right, so now this equation right here, I've just numbered it. There's nothing special. I haven't changed anything. All I've done is I've given it a number. And since I've noted I want to discretize it, I'm going to do the following. I'm going to remove the little o portion of this. I'm going to let epsilon simply be fixed. Once I do that, I get an equation 4.2, which looks almost the same, but now we no longer assume that epsilon is going to be changing. We really want v epsilon that's going to satisfy that equation. And that equation for us is going to be the DPP, the dynamic programming principle, which sounds very ostentatious. Once again, I'm going to pay a little bit of lip service to some of the stuff you'll see in the papers. They don't always agree. Sometimes the DPP for a game is going to be exactly this, one equation line, and that's it. And then later on, they'll introduce separately boundary conditions. Sometimes you'll see the paper introduce this sort of equation and then boundary conditions all at the same time and claim that to be the DPP. Part of that just comes down to author preference. Some of that's going to come down to when you can actually find solutions of the DPP, which I mention over here on this next page. So when does var epsilon exist? One way to do it is to rely on a paper of Liu and Sikora. I don't know where Liu is based. I think possibly at Pittsburgh, but Sikora definitely is based at Pittsburgh along with Marta and Juan. And that paper gives some very general conditions under which you can show that a DPP posed as both an equation and a boundary condition has a solution. In a lot of senses, that actually comes back to something like Perron's method, which I know will make Nathan very happy because he always likes Perron's method when I talk. You always bring it up. Don't give me that look. For another good example, though, you can also do it without having to use that paper of Liu and Sikora. If you look at the paper, which is by Manfredi, Parvianen, and Rossi, then you actually can see an example of them proving it without using Liu and Sikora's criteria. And in that case, they pose the DPP exactly as that one equation and nothing else. And then boundary conditions are introduced later as necessary. So okay, we have some ways to find out whether or not var epsilon exists, which is good for us. But if you were paying attention and reading and not just dozing and listening to my dulcet tones, then you probably noticed that I mentioned somewhere on the previous page that var epsilon needs to satisfy some kind of relationship with what we are doing in the epsilon games. So a really great question would be, what relationship? Well, this is where we have to go and make use of almost optimizing strategies. So let's back up to the game again, and let's think about what happened. Now, if we go back to the definition of the game, where we started all this mess for the p-Laplacian, we'll notice that there were two players. Each of those players, player 1 and player 2, has a certain goal. Since we were talking about Nathan and me before, let's just continue that rivalry. One of us wants to make money off of the other. That's as simple as it is. Nathan wants to gamble me out of house and home, and I'd like to do likewise for Nathan because we're loving and enlightened mathematicians. In order to encode that, what we're going to do is we're going to define functions which we'll call U1 and U2. U1 and U2 are going to be based off of the ordered pair of our strategies, which we're just going to denote by sigma for ease of use in our equations here. And so you can see how we're encoding them directly. U1, if I'm player 1, I would like to first, if I possibly can, make sure that Nathan does as poorly as he possibly can, and then I'd like to ensure that I do really, really well. Nathan, on the other hand, would like to make sure I do as poorly as possible, and then he'd like to make sure that he does as well as possible. We're also going to give an expected value to the game, which we're going to denote by U sigma. And U sigma is just going to be, we pick strategies T1 and T2. We don't worry about taking the best or the worst. There's just two strategies. We put them into our game, and we find an expected value for f of x tau, where I'll remind you x tau is the ending position of the game if we start at the point x. What we're going to do is we're going to show that every single one of these three functions is actually the same, and that they satisfy the dynamic programming principle for our game. If we can do that, and if we can do that for every single epsilon, then we can invoke conditions upon the geometry and theorems or lemmas that maybe are something like Arzela-Ascoli. Again, I'm being very vague purposefully. And we can show, under the right conditions, the family of functions which unify those three apparently separate functions and also satisfy our dynamic programming principle are going to have a convergent subsequence, and they're going to converge to a solution to our p-Laplace equation. That's the idea anyways. But this is where we're going to need the strategies. So let's do this. Let's just say we have found a function v epsilon which satisfies the DPP which we gave before. Let's say that we have a given value, eta greater than 0, and let's say that I choose any strategy whatsoever. It doesn't really matter what the strategy is. I'm going to call it T, and I'm going to say the maps that make up T, they're just going to be called sigma for right now. Nathan, on the other hand, is going to try to play by a strategy which we hope exists. Hope is a key word in this theory, which we're going to call T underline or T underbar. And it's going to have maps sigma underbar with a certain special property for us, the almost optimizing property, which is equation 4.3. Basically, whenever you have a position xn that's already given in the game, and you, Nathan, apply your strategy to figure out where you're going to move next, the strategy is going to give you a point which is so small that it's less than or equal to the infimum of all of the values among the possible places we could move, adjusted by adding eta over 2 to the power of n. Okay? Weird formula, but okay. It doesn't seem particularly motivated yet. But I am a wizard, or rather, Manfredi, Parvianen, and Rossi are wizards. We have a lemma, which is due to them. With the conditions that we've given above, the sequence v of xn, really it should be v epsilon of xn. I'm going to have to annotate again. Thank God for me. V epsilon xn plus eta over 2 to the n is actually going to be a super martingale for us. Super martingale, you say, your ears perking up. Why, this sounds like things we've already talked about. And yes, yes it is. The proof also relies upon things that we've already talked about. Also, you're going to have to use your imagination now because the epsilon is going away to make room for other things. So what is the proof? Well, the proof is actually pretty straightforward. If we've already found the points x0 through xn minus 1, they're already known and fixed. When we try to take the expected value of this sequence, which we claim is a super martingale, what's going to happen is we're just going to integrate what's inside that expectation symbol with respect to the measure that we're dealing with right now. And as it turns out, the measure that we're dealing with right now at this step is nothing more or less than little gamma of x0 through xn minus 1. When we integrate with respect to that measure, there are three parts. The parts that are Dirac delta measures with respect to the points that I choose, which would be their epsilon, v epsilon of sigma of xn minus 1, and a point that pays respect to where Nathan wants to go with his almost optimizing strategy, sigma underbar. And then there is also the completely random component, which neither of us control, which is associated with the coefficient beta and simply involves us integrating over the ball of radius epsilon based at x minus 1. And you'll notice now that just this eta over 2 to the n, that simply comes about because it was hanging out inside the epsilon, the expectation symbol anyway. It's rude not to include it. Now, to go from this line of equality to this inequality is a very simple observation. All we do is the following. Clearly, the first part, the part over which I have control, increases if we took the supremum of their epsilon over the ball of radius epsilon centered at xn minus 1. For Nathan here, because of his strategy, that value that he's going to get out of v epsilon is going to be less than or equal to the infimum of v epsilon over the ball, the same ball, if we just add eta over 2 to the n. So now we have a supremum of v epsilon over the ball, an infimum of v epsilon over the ball, and we actually also have an averaged integral over the ball. Now wait a second. We said v epsilon satisfies our dynamic programming principle. So what was that? It was equation 4.2. And equation 4.2 is composed exactly of the pieces that I named. The only difference between what we have in our current situation is that we have 2 copies of eta over 2 to the n. Well, what's going to happen then is all the information that goes along with that dynamic programming principle is going to come together and collapse down to v epsilon at xn minus 1. And the 2 copies of eta over 2 to the n are going to add together and simply give us eta to the 2 to the n minus 1, which is the previous term in our supposed martingale. Therefore, we have proven this sequence of functions is in fact a super martingale. Cool. Now we have another lemma. With all of the same considerations as before, and one extra one, which is simply the boundary conditions I've been paying lip service to for a little while. We assume all of the same stuff as before, but v epsilon is also going to be greater than or equal to u2, Nathan's value function on the boundary. Then it turns out that v epsilon is actually greater than or equal to u2, which I think is pretty easy nowadays. I don't even know what u2 has been doing. Inside of D. What's the proof? Well, here's the proof. All of this is pretty easy to follow. It comes directly from the definitions. The only thing that is not necessarily easy to follow is the step that goes from the second inequality to the third inequality in our line. The reason that that part is a little bit weird is that we're treating tau as if it's a stopping time. And as I mentioned before, it's hard to say without doing more work that tau is a stopping time as we've defined it. Because if you'll recall, tau is just the infimum of all of the indices for which xn belongs to the boundary, belongs to y. Well, this is where that corollary in the very beginning, all those eons ago, comes into play. We simply pass to the increasing sequence of actual stopping times, tau, wedge the constant stopping time n, and we use Fatu's lemma. Doing that, we pass very easily from the second inequality to the third inequality. And then we simply use the properties of the very last, or second to last line to declare that u2 is less than or equal to v epsilon at x plus arbitrary eta, which proves our lemma. So much for the technical stuff. We can do that again. We can do that again exactly for my value function u1. And I'm going to have to annotate again because I love it so much and also because apparently I'm prone to mistakes. This is v epsilon here, not just random epsilon. And as a result of all these things, where once again, you're going to have to use some of that imagination, be brave, we're going to find the expected value for the game is exactly the same as the value functions u1 and u2 is exactly the same as v epsilon that we've talked about before. So in other words, the expected value of the game is a function which satisfies the dynamic programming principle and takes the boundary data f on y. How are we doing so far? People good? Nathan's good. We're running close to time. Okay, so this is great because now I'm not going to introduce a lot of details. We've reached the part where things are going to get a little bit hectic if we try and go too in depth. So we've already talked about the fact we can't really talk too much about convergence. That's going to be too much for this talk, especially with the time we've got left. So instead, we're just going to talk about the notion of solution. I've already said that when v epsilons converge to v, we're going to wind up with a continuous function. And usually a continuous function does not solve a second order differential equation. Definitely it doesn't do so classically. So the question is, how are we saying it solves it? Well, gliding through the definition of what we're going to call proper and degenerate elliptic equations, I'll simply say the words and say we're going to be focusing on those sorts of equations. And you can look at this definition here if you're more interested. It turns out that for degenerate elliptic and proper equations, like the L that I've noted right here, we can define what we call viscosity solutions. What are they? Well, they're just continuous functions with the property that at any point in our boundary, if we can find C2 functions which touch our continuous function from above or below, which is what the second equation line is talking about, we simply replace the function v in our second order differential equation with the C2 function phi and see that it verifies the inequalities in the very last line. As long as that happens for every single touching function, whether it touches v from above or below at the point x, then we are willing to say that v is a viscosity solution. And we can think of it just as the touching functions being test functions, almost like you would do for weak solutions, and we're pushing the derivative properties off onto these test functions. There are a lot of really good reasons to use this theory, which I'm going to breeze through very, very quickly. I'm only going to mention one because I'm going to continue to tease Nathan about Perron's method and say that Perron's method can be shown to hold for proper and degenerate elliptic partial differential equations of second order, and so that's nice. In other words, if we can find sub and super solutions which are equal on the boundary of our domain, then we can find a solution in the viscosity sense. And because of this, and because of the fact that our functions v epsilon converge to a continuous function, it makes sense to use the notion of viscosity solutions in order to solve these differential equations. And that's exactly what happens. You can look at Manfredi, Parvianen, and Rossi for details for the p-Laplace equation. And also you can actually look at Blanc, Manfredi, and Rossi for the Pucci's maximal operator case. Basically, all we do at the end of the game is prove that when you have touching functions, the touching functions satisfy the viscosity definition that we put up on the board just a mere moment ago. And that is it for me. I've talked your ear off enough.
All right, thanks. So I still don't know how to do this non-awkwardly, so I'll clap. But
you're supposed to say thank the speaker and just eat the awkwardness, Nathan. Now it's more awkward.
So anyways, does anyone have any questions? If not, I have a few, but does anyone else have questions first?
Nope.
I like it. Succinct.
Everything was 100% clear.
That's because I'm a wizard, as aforementioned.
Yes.
So I have maybe, well, I'll ask one question.
Okay.
So your equation 4.2, which was this dynamic programming principle, could you go back to that?
Yeah, let's go there. It'll be nice to see where we're going. Oh, it's not that far away. I am a wizard. There you go.
So so question one, which is sort of just an understanding question. Do alpha and beta depend on, so first they should depend on p, you said?
Yes, they do.
They depend on the dimension as well, or?
Yes, they do depend upon the dimension. I think I touched upon that briefly. Let me back up just a little bit further to where, excuse me, we talked about the results of the games. Yes. So
Yeah.
you can see here in beta, well, actually in both of them, the dimension of the game also plays a role in this. So it depends upon where you're playing the game.
Okay, so it does depend on the dimension. So my question was, there seems to be an obvious extension to something like graphs. So you could do, there's an analogous version of graph Laplacian. I was wondering if you could do the same thing for, well, p-Laplace. Is there an extension using this sort of programming principle? But dimension I don't know how to account for. If it was just depending on p, then it would make sense, I think. But this dependence on n, I don't know.
So let me see. If I'm understanding your question, you're talking about the idea of somehow extending the p-Laplace idea that we've got here to a graph. Maybe
yeah,
like
so there's a notion of graph Laplacian. It gives information, and you can.
I do believe that there is some information around about that. I don't typically play with graphs. In fact, I've more or less dipped my toes in here, reached almost optimizing strategies, and found that they are a pain to prove that they exist. And so far, I've dipped back out with the hope and the promise that I will dip back in as soon as I'm able. But if I recall, I believe that the last section of Manfredi's contribution to the book I mentioned earlier actually talks a little bit about some of the papers in which the idea of graphs was examined. So yeah, I think it either falls under section 5 for that contribution, which is called Directed Trees, or else possibly under, let's see, Discrete Laplacian pops up there, and also there's an epilogue, which I believe talks about it as well. So that would be a good resource for you to check it out and see.
Okay, I'll have to go and look. So thanks.
You're welcome.
So I have a couple other questions, but I'll maybe ask later. So let's thank our speaker one more time, and then we can just talk. So.
Okay. Yay.
So I see Anna showed up.
So I have a thank you for attending there at the very end, because I'm not one to skip formalities, at least not entirely, as shown by earlier. And then here I'll just take a moment to point you at some of the resources I have. Anybody who would like to have this slideshow is more than welcome to have it, particularly once I've gone and fixed in all those things I had to fix in medias res.
Send them. Oh.
Is there some way that you, I mean, can you send it to, I don't know. Could you send it to me if you can remember?
On the website, Brittany, I think. So Zach, if you want to send it your updated slides whenever you get the chance to update. I think, you can post it to the website?
Yeah, sure.
Okay, so.
I'd be happy to do that.
Okay, great. Thank you.
You're welcome.
And did you guys record this lecture this time? Because I see the little recording.
Yeah, it's recording. Maybe
Okay.
I'll stop the recording now.
Yeah.